All right, good morning. We're going to get started. So hopefully all of you are able to find the video with the continuation of Monday's lecture after my internet went out. I made an arithmetic error and thought I had 5 more minutes left than I actually did. So I'm sorry that it went a little bit over on Monday, but this is why I don't take off a lot of points on exams for arithmetic mistakes, because I can't really do it either. So anyway, hopefully we'll have a smoother go of it today and we won't have any technical difficulties. So let's start into what we're going to do today.
Oh my gosh.
All right, so last time we got through quite a bit, actually.
Okay.
Yeah, agreed, Jenna.
Okay. Thank you for calling. I think
My wife was upset
the
because
scratches are fine.
she was like, "You're not supposed to swear in front of students," and I said I didn't, and I censored myself.
He was fine listening.
Anyway, last time we got through a few things. We started chapter 7 on vapor power systems. We talked about vapor power plants and why it's important that we study them. We discussed the Rankine cycle, which is how we model the processes that occur in a vapor power plant. We defined a couple things. Really, we've seen thermal efficiency before for power cycles, but we were able to write it in terms of the enthalpy at every state for the Rankine cycle. So all we need to do basically to analyze the Rankine cycle is compute the enthalpy at all 4 states. And there you go. At least for the ideal case, with a simple cycle. We define the backwork ratio, which is the power output from the turbine divided by the power input to the pump, singular. And then we started an example looking at ideal Rankine cycle performance. So we'll finish that today, coming up next here. And then we'll do a couple other things. So we'll look at the effects of the boiler and condenser pressure on performance of the system. We will make a comparison of the Rankine cycle to the Carnot cycle, the ideal Rankine cycle to the Carnot cycle. And then we'll introduce the possibility of having irreversibilities and losses in the system and do a bit of analysis on that. Okay. So let's get back to it today. So this is sort of like what I had done on the remainder of the video yesterday, or on Monday, I'm sorry. So I think this is as far as we'd gotten before the video cut out, and then we got to, I wrote down all the things we need to find. And as I said before, we just needed the enthalpy at all 4 states. So we know how to do this already. We have details on the processes. There's 2 constant pressure processes from 4 to 1 and from 3 to 2. And then 2 isentropic processes from 1 to 2 and from 3 to 4. And so we know how to do this. We know how to do this, how to get the enthalpy at every state. So we go through and use RefProp, right, and get the enthalpy at all 4 states. And then we pretty much just plugged it into the definition. So even if you missed the rest of the video, honestly, you didn't miss that much. There was nothing groundbreaking that happened. We found the enthalpy at every state, and then we plugged it into the formulas for efficiency and found that the cycle was 37% efficient. The backwork ratio was 0.84%, really small. And then we used the power, the net power, which we were given as 100 megawatts, to compute the mass flow rate of the steam, because we could write these 2 ratios as a difference of the enthalpies. And so we could write out this expression with the 4 enthalpies, the net power, and the mass flow rate, solve it for the mass flow rate, plug in our numbers, and then compute the mass flow rate. Okay, so what remains to do to finish this problem is to find the heat transfer in to the boiler, the heat transfer out through the condenser, and then the mass flow rate of the cooling water. So that's where we're going to pick up right here. So part D, Q dot in, we wrote down this formula already when we were introducing the cycle. It's the mass flow rate of the steam times H1 minus H4, the enthalpy difference between post boiler and pre-boiler. And we just calculated the mass flow rate of the steam. We already have our enthalpies, so we can just plug in numbers. 104.7 kilograms per second is the mass flow rate. And then the enthalpies are 2758.7. When you work these problems, you end up seeing the same numbers over and over again, so you kind of memorize them almost. And 181.84, and those are enthalpies, so they're kilojoules per kilogram. And so when you put this together, put it in your calculator, you get that the heat that you have to add is 269.8 megawatts. All right, likewise for Q dot out. We have this formula already, m dot S times H2 minus H3. So the enthalpy going into the condenser minus the enthalpy going out, because the enthalpy drops for the steam going into the condenser. So again, just plugging in numbers, 104.7 kilograms per second times 1795.1 minus 173.84. Those are in kilojoules per kilogram. And this comes out to be 169.75 megawatts. And then we need to find, the last thing is to find the mass flow rate of the steam, or sorry, the cooling water. So to do that, we will treat the condenser as a heat exchanger, because that's really what it is. We're flowing the steam through the condenser, condensing the liquid, and then to do that, to enact that condensation, we're flowing cooling water through the other side. And so we can set up this expression for the heat exchanger. On the one side, we have the steam going through the condenser. So we have m dot S H2 minus H3, right? That's actually Q dot out. That's the heat being extracted from the steam. And then on the other side, we have to have the heat being absorbed by the cooling water. So this is m dot C, that's what we're after, times HC going out. So the enthalpy of the cooling water going out minus the enthalpy of the cooling water coming in. Okay, so the order of these two, I just sort of do it in my head. I don't really like memorize a formula, because memorization can get you into trouble. It's more important to understand the principles. So here, this number is positive. So if I want this side to be positive, I need the bigger one to be the positive one and the smaller one to be the negative one, right? When I subtract them, I have to have the bigger one minus the smaller one to get a positive number. Yeah. And so since it's absorbing heat, the enthalpy going out is going to be higher than the enthalpy coming in. Okay, so that's how I think about it when I write down the order, to make sure that I don't screw up my signs. All right, so to get these, I can either assume that the pressure is about 1 atmosphere. That's a reasonably good guess, because usually the cooling water is like, a lot of times you'll even just have a river or something flowing by, and you just sort of dunk your condenser in the river, or you siphon some of the flow off or whatever, but you don't pump the pressure up or anything. So you could either assume the pressure is 1 atmosphere, I gave you the temperatures, and use that to get the states, or treat it as an incompressible substance because it remains a liquid, and just use a specific heat of 4.18 joules per kilogram Kelvin, which is the specific heat of liquid water. And then for our incompressible assumption, we have that delta H equals C delta T. Right, so we could do either one of these. I'll use the second one because it's a little simpler. I don't have to go back to ref prop. So I'll solve this expression for m dot C and substitute this for it. So m dot c equals m dot s times H2 minus H3 divided by, and then it's going to be C, the specific heat, times TC going out minus TC coming in. So the temperature of the cooling water going out minus the temperature of the cooling water coming in, right? And I can recognize, of course, that this is just Q dot out, which we already solved for, divided by C times the change in the temperature of the cooling water, which I believe was given to us. Did I give you the change or did I give you the two temperatures? Well, so there it is. Comes in as 15 and leaves at 35 degrees C, but you convert those to Kelvin. So I have all the numbers now. M dot C is going to be, I found this one already, is 169.75. This is in megawatts, and I'm probably going to want this. Oh, I'm sorry. This is C is, that's the 4.18. That's in kilojoules per kilogram, right? It's joules per gram or kilojoules per kilogram. So this is in kilojoules per kilogram here. So I probably want this in kilowatts. So that way everybody's on the same basis. So I'll just multiply by 10 to the 3 there. So now this is in kilowatts. Divided by 4.18 kilojoules per kilogram Kelvin, right? There's C, times, and then delta T is 20 Kelvin. That's the temperature difference between the two. Okay, plug all this into your calculator and you get, that's not a number, 2.03 times 10 to the 3 kilograms per second. So that's like 2 metric tons of water per second to cool this steam off. Tremendous amount of flow, right? It might be easiest actually to think about this in terms of how many cubic meters per second. So the density of water is like, it's 1,000, right? 1,000 kilograms per cubic meter. It's 1 kilogram per liter. And there's, a liter is a cubic deciliter. Sorry, a liter is a cubic decimeter. So yeah, 1,000. Yeah, 1,000 kilograms per cubic meter. So that means that this is 2 cubic meters of water every second going through the power plant to cool it off. So like I said, tremendous amount of water needed to cool these things. Okay. So that's finishing off that example. I think there's one of those on your homework, something similar to that, an ideal Rankine cycle type problem. Okay, so now the next thing is we'll look at the effects of boiler and condenser pressure on performance. So the first thing I want us to notice is that the heating in the boiler is not isothermal. So somewhere I have, yeah, hold on, it's on the fort, got it. This was our TS diagram, right? So the heating in the boiler occurs at constant pressure, but because we start out over here, we're a compressed liquid, we follow an isobar, which means that the temperature goes up and then you hit saturation and then it's constant. So it's not constant, right? So this heating is isobaric, not isothermal. Okay, but we won't let that stop us. We can write that the heat coming into the boiler divided by the mass flow rate of the steam because in an ideal Rankine cycle, this is internally reversible, we can write this as the integral from 4 to 1 of T ds, right? Just like we saw for in chapter 6 when we talked about entropy. So using some calculus, and really all this is the definition of the average or the mean value of a function. So if you look that up, how do you calculate the mean value of a function, which you should have done in Calc 122, Math 122. We can write this as Q dot in over M dot, which is internally reversible, equals the average temperature during this process from 4 to 1 as the heat's coming in. So that's why I wrote T in. So the average times the entropy difference. Okay, so this integral equals this. That's just from the definition of the mean value of a function. I didn't do anything fancy, right? So we could do the same thing for Q dot out, but in this case, Q dot out is isothermal, so we don't have to. So I can use this to write that the efficiency of the ideal Rankine cycle, which is equal to 1 minus Q dot out over Q dot in. I haven't done anything yet. This is the same definition. Okay, if I take this away, that's the same definition we've always had for efficiency, right? We should recognize this. We saw this in like chapter 2, one of the first ones, right? So this shouldn't be new to us. Now all I'm saying is it's an ideal Rankine cycle, so these are internally reversible. But I still haven't really done anything interesting yet, right? But now I can write this in terms of the temperatures. Okay, so this is going to be 1 minus T bar out over T bar in. So what do I draw from this? I can eliminate, by the way, if you're wondering, you can eliminate the entropy differences because if you look at the diagram, what was it? If you look at the diagram, because these two processes are isentropic, S1 minus S4, which is like this horizontal distance on the TS diagram, is the same as S2 minus S3, which is this horizontal difference. So the entropy differences cancel out. That's why I don't need those. I just read it in terms of the temperature. So the efficiency increases for T out going down, right? Because we want to make this thing smaller. So if T out goes down, this fraction will get smaller. And T in going up, all right? This is a lot like what we saw for Carnot engines, right? Where you want to spread out that temperature difference over which your cycle is occurring. Except here we're writing the average temperatures. Okay, so we have this in hand now, all right? So we see we can increase the efficiency by lowering the temperature at which we extract heat and increasing the temperature in the boiler. Okay, so now let's look at the pressure of the boiler and the condenser. Okay, so let's do the boiler first. So I'm going to sketch this on a TS diagram here. We have our saturation curve, which looks kind of like that. I'm going to draw in our regular Rankine cycle, 1, 2, 3, 4. So 1, 2, 3, 4, and then to get from 4 to 1, you kind of go across like this, hit that intermediate point where it saturates, and then go straight across. All right, so let's say that this isobar here is P1. What if we increased the boiler pressure? Okay, so if we increase the boiler pressure to say P1 prime, all right, then this isobar is now going to intersect here at state 1 prime, come down to 2 prime. Okay, we're still going to go across the same 3, but now we have to get up to this isobar. So we have to go up to 4 prime, and then you come across here, and then straight across once you hit saturation, right? Okay, so I've basically just drawn 2 different cycles, but at different boiler pressures. One at 1 and the other one at 1 prime, where 1 prime is higher than 1. Okay, so I look at the effect of doing this. The effect of doing this is that increasing P1 to P1 prime, it increases the average Tn, right? So that if you look at like this 2 lines and then these 2 lines, the average temperature of these 2 lines where the pressure is P1 prime is higher than it is for P1. So increasing the boiler pressure has increased that temperature. And as we saw from above, that will then increase the performance. All right, so this, in fact, sorry, just adjusting the camera a little bit. So this is limited then by material properties. You know, how much pressure can your boiler actually withstand before it would rupture? Or if you have really strong material, or let's just like really thick walls on your boiler, the other thing limiting this would be the critical pressure of your working fluid, right? Which is where the isobar would cross that point right up there. You wouldn't actually get any boiling at all. You just have supercritical fluid, and then you wouldn't really be in a Rankine cycle anymore. So the critical pressure, for instance, would be 22 megapascal for water. Okay, so in the early days, this is one of the reasons why steam engines were not that efficient in the early days, was because they didn't have great materials to make their tanks out of. And so they weren't as strong as they could be, so they couldn't really increase the pressure too much. Nowadays, we can get, 10 megapascal is not a challenge really. We can easily hit 10, 15, 20 megapascal. There's even supercritical power plants that go up above the critical point, the critical pressure. So that's not so much of a barrier to us anymore, but it is of course more expensive to make something that can withstand higher pressure. So there's always that trade-off as well. Okay. Now let's look at lowering the temperature in the condenser. The pressure in the condenser. So we saw, I'm giving things away. We saw that increasing the pressure in the boiler increases the temperature and therefore the performance. So let's look at what happens when you change the pressure in the condenser. So I'm going to redraw our TS diagram. I'll put on our 4 original points. So here's 1, 2, 3, 4, and then we connect these like this. There you go. All right, so let's say that this is P2, and then let's go down. Let's just go down to a lower pressure, P2 prime. Okay, so this isobar now comes across like this, straight across, right? So we have to stay at constant entropy from state 1, so we come down straight line to here. This is now 2 prime. And then we come across to 3 prime. Okay, and then we go straight up from here to this same isobar. So we actually connect a little bit further back. So let me remove where 4 is. 4 is here, and then this would be 4 prime here. So you connect just a little bit further back along the isobar there because you're at slightly lower entropy at this state because of the slope of this saturation curve. Okay, so that's the effect of lowering the pressure in the condenser. So we see that lowering the condenser pressure lowers the average temperature in the condenser, which, as we saw before, increases the performance. Okay, so you want a high pressure in the boiler, low pressure in the condenser. That's what gets you good performance because the temperature at which water boils is a function of pressure. If you have higher pressure, the water will boil at a hotter temperature. If you have a lower pressure, the water will boil at a lower temperature. Okay, and just for practical concerns, because we don't, we don't build power plants inside of like freezers or something, the lowest condenser pressure possible, this is not limited by material concerns because we can build vacuum chambers. Those are actually pretty easy. 1 atmospheric pressure difference is basically nothing. So materials can withstand vacuum, no problem, most of the time. I mean, unless they're like a aluminum can or something, but like normal structures can withstand a vacuum. It's pretty simple structurally to do. So the lowest pressure possible we're limited by is the fact that we have to get heat transfer out. We have to be hotter than whatever the temperature of our cooling water is, which is usually ambient temperature. So it's the temperature or the pressure at which the corresponding saturation temperature is about equal to the atmospheric temperature in order to get heat transfer. And that happens to occur around a pressure of 3 kilopascal. Okay, so if you did this at atmospheric pressure, so if you had an open condenser, okay, where you're just sort of like spraying water onto your condenser or something, or just like letting the water like condense in the atmosphere and then collecting it or something, or having like an open loop system, something like that, then this pressure is atmospheric, P2, and then your temperature in the condenser is 100 degrees C instead of like 30 or 40. Okay, so having an actual closed condenser where the water is allowed to condense at lower pressure instead of having to condense it at atmospheric pressure, that concept, that was the innovation that James Watt made. So I made this reference a long time ago that like James Watt, the reason why he's famous is because, and why we have a unit named after him is because he made a much improved version of the steam engine. And I told you back then that we'd talk about what that was and you'd be able to understand it. So this is what he did. This was his innovation, was he invented a steam engine that had a closed condenser so that that condensation could occur at a lower pressure and therefore lower temperature. And so the innovation of Watt increased the theoretical efficiency of an ideal cycle from about 5%, so 5% efficient, that was the best you could do, to 25%. A huge jump, okay? But the actual, I'll just, as a side note, the actual efficiency was about doubled because there were still a lot of losses and stuff. The turbine and pump were not very efficient, and so there were a lot of other losses. So the total efficiency was actually about doubled. But still, that's huge, right? That's a massive improvement. you could get twice as much power for the same amount of fuel, or the same amount of fuel for only, sorry, the same amount of power for only half the fuel. So massive, massive improvement. One other note about this, historical note before we move on, is this occurred, James Watt's work occurred in the 1770s. If you remember from when we were talking about the second law, Carnot, who came up with this idea that the efficiency of steam engines was a function of the ratio of the temperatures, and that's what sort of has motivated all of this, right? That you want to get that higher temperature here and the lower temperature here, right? That wasn't even written down until 1824. And remember, people didn't really appreciate it until Kelvin and Clausius put it together a couple decades later. So James Watt made this innovation 50 years before the fundamental idea of why it worked was written down. Watt was just an engineer. He was just monkeying around and happened to figure out something that improved the efficiency. He didn't understand why, but he didn't have to. So this is kind of like one of those things that's, in retrospect, is kind of fun to think about. And also it gives us a bit of a model of like different types of thinking for scientists versus engineers versus people who kind of sit in the middle of the space, who can understand the fundamental principles of why the innovation is helping, and other folks who are just experimenters, sort of like Edison, right? So Edison didn't understand anything about electricity really, but he invented all this stuff just because he was so doggedly determined to get it right. Okay, so that's the effect of pressure in the condenser and the boiler. So the next thing that we're going to discuss is a comparison to the Carnot cycle. So before we do this, I want to do a poll. So get your thinking caps ready. All right, so our poll for today is an ideal Rankine cycle, where everything is internally reversible, equivalent to a Carnot cycle? So you got four options here. Yes, because all four processes are internally reversible. Yes, because the turbine and the pump are isentropic. No, because the working fluid is undergoing a phase change. Or no, the heat transfers occur at constant pressure, not constant temperature. So you may have to go back, flip back, and look up your definition of a Carnot cycle if you can't remember. But so think about this and put in your answer. Yeah, speaking of the monkeying around and getting lucky and stuff, my PhD advisor he was sort of an older guy from Florida, and so he had all these folksy sayings. And one of his favorites was, "It's better to be lucky than good." And I don't know if I should say I've taken that to heart or not, but that's one that sticks with me, because oftentimes that is absolutely correct. I'll wait for just a couple more responses to come in, then we'll have a look. Okay. Yay. Okay. This is about what I expected. So we had the most popular answers were A and D, but most folks got the majority got the correct answer, which is D. So the four processes are internally reversible, but remember, the Carnot cycle is a very specific type of reversible cycle, where you have adiabatic expansion and compression, and then in between those you have isothermal heat addition and removal. And in the Rankine cycle, we don't have isothermal heat addition and removal. We have isobaric, so constant pressure heat addition and removal. So we could get a Carnot cycle. I'll show you this in a second, but so hold on, I'll take a timeout on that. So as I was saying, so the heating is not isothermal. So the ideal Rankine cycle is not a Carnot cycle. Furthermore, we can see that the average temperature on the hot side, so the average temperature of the boiler, is less than the maximum temperature that occurs in the hot side. Okay, so the efficiency is not as high as a Carnot cycle. Because remember, the Carnot cycle has the maximum efficiency for any heat engine between the same two maximum and minimum temperatures. Okay, so we could do it as a Carnot cycle, actually, with isobaric heat addition and removal if we had our four states like this. 1, 2, sorry, this is 4, 4, straight down, 2, 3, and up. So if we did it in there, instead of taking this all the way out to saturation, I think there was a question about this on Monday, actually. If you didn't take 3 all the way out to saturation, then when you go up to 4, which is at saturation, then your constant pressure heat addition is also constant temperature heat addition. And then you could have a Carnot cycle. Okay, but we can't do this for practical reasons. As we discussed before, basically pumps don't work on two-phase mixtures. They need a liquid. They won't compress a gas. You need a compressor to compress a gas, but a compressor won't work on a liquid. So two-phase mixtures are kind of like the devil in Rankine cycles. We don't want to do anything with them other than condense or boil them. We don't want to put them through a turbine or a compressor or pump. Okay, so now let's talk about principal irreversibilities. And losses. So the first thing that should be said here is that there are external irreversibilities most notably those involved in combustion and the heat transfer itself, Q in, from the hot combustion products or whatever your heat source is to the working fluid, right? Because this will work. Okay, so remember, a reversible heat transfer is one that occurs over an infinitesimal temperature difference. If you have a finite temperature difference, that heat transfer is irreversible. Okay, so even if your hot stuff was infinitesimally larger than this temperature, than that saturation temperature right there, you would then create a finite temperature difference in this region. Okay, so there's irreversibility associated there. But most often, because we want the heat transfer to happen faster, our temperature in the combustion products or whatever our heat source is actually much higher than this. Okay, so it's way up here somewhere. So that heat transfer is occurring over a fairly large finite temperature difference. So even if internally in the steam, all these changes are internally reversible, there are a lot of external irreversibilities going on in the heat transfer process. Not to mention if you have a fossil fuel plant in the combustion of the whatever's generating your heat. Okay, but we will not consider these. These are considerably more tricky to model, and they're actually handled in the chapter that we skipped in Moran, because it's not that important for you guys to understand at this juncture. So we're just going to look at the irreversibilities that are internal to our system. We're going to ignore the ones that are happening on the heating side. Okay, so primarily the irreversibilities we consider are those in the turbine and pump. There's an M in there. Sorry, pump, which is what we saw in chapter 6, right? We know how to handle isentropic efficiency for turbines, pumps, compressors. Okay, you also get a degradation of performance from like stray heat transfer through the piping, friction of the fluid through the pipes. So you get pressure losses in the boiler and the condenser, for instance. But typically those are pretty small, and hence these irreversibilities in the turbine and pump are the ones that are the most important. Okay, overall, and so those are the ones we're really going to focus on. So we've seen these relations before, but I'm just going to write them back down so that we remember them. The isentropic efficiency for a turbine, remember, is the power that you get out of it per unit mass, or not per unit mass, whatever, depending how you want to normalize it, divided by the power you would have gotten out if it were isentropic. And we can write this in terms of the enthalpies as H1 minus H2 divided by H1 minus H2S. And remember, H2S is just that imaginary state that would be at the same exit pressure for the turbine if the turbine were isentropic. So you take state 1, and then you say, I'm going to hold the following, I'm going to hold the pressure at state 2. That's one of my properties. And then the entropy, I'll hold that constant. So my two properties to compute that isentropic state, that imaginary isentropic state, are the pressure and the entropy. And then for the pump, A to P equals the power you have to put into the pump if it were isentropic divided by the power you actually have to put into the pump. Because isentropic is sort of like ideal, so it's less power that you'd actually have to put in than you'd have to put in less power than you actually do. So again, I can write this in terms of the enthalpies, H4S, which is that imaginary state 4 if the pump were isentropic, minus H3 divided by H4 minus H3. So let me sketch what this looks like on a TS diagram. What do I do with my, yeah. All right, so I'll draw our familiar ideal cycle, except the ideal cycle is going to have the isentropic ones on it. So instead of going straight down from 1 to 2, I'm going to come straight down now to 2S. Okay, go across to 3. 3 is still the same. And then straight up, and instead of, I'm going to exaggerate this a lot. So come way up. Normally, I mean, the isobar actually hugs the saturation curve pretty closely, but I'm going to go way up just to exaggerate it. This is now 4S. That's our isentropic pump. And then we follow the isobar across to close our little box back to 1. So what actually happens is state 2 through the turbine, the entropy is going to increase a little bit, but we're at the same exit pressure, which means that we stick to the same isobar. So the actual state 2 is going to be over here somewhere, and I'll draw this in with a dash line. Okay, so state 2 is actually over here. And then likewise, state 4 is going to be along the same isobar, but at increased entropy. So state 4 will be up here somewhere. Right? And the closer you are to isentropic, the closer these dash lines get to being vertical, to matching up with 2s and 4s. Okay. So I'm gonna set up an example, and then we'll solve it at the beginning of class on Friday. Okay. So we'll do the same Rankine cycle as before, but with A to T and A to P, the efficiencies of the pumps, the pump and the turbine being 85% instead of 100% efficient. They'll be 85% efficient. So to finish the setup, I'm just going to point out that because everything is between the same limits, between the same pressures, and at the same, same total power and blah, 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 all same pressure limits. I already said that, same pressure limits. All our enthalpy values are the same, except what used to be H2 and H4 in the previous example are now H2S and H4S. I've just relabeled them because those are now the isentropic enthalpies, because before we were doing an ideal cycle where everything was isentropic, well, where the pump and the turbine were isentropic. So I'll just recopy those numbers right back down instead of doing any work to actually look them up, because I already did this example. H1 is 2758.7 kilojoules per kilogram. H2S now is 1795.1 kilojoules per kilogram. H3 is 173.84 kilojoules per kilogram, and then H4S now is 181.89 kilojoules per kilogram. All right, and so what we're going to do is just use the definitions of the isentropic efficiencies to compute H2, the real H2, and H4, the real H4, given the isentropic efficiencies. And then from there, it's just plugging the numbers in again and computing, the overall thermal efficiency, backwork ratio, m.s, the heat transfers, and the mass flow rate of the steam, which is exactly what we did at the beginning of class today, except we'll be doing it with slightly different numbers. And we'll take a look at what happens to the performance. Okay, so that's it for today. I will see you guys all on Friday.